So, first of all, good morning, good afternoon, and good evening, wherever you are in the world joining us. To those who have been to a Weidmann webinar before, we very much welcome you back. And to those that this is your first webinar, welcome. We have a large number of people on the call, and to those that are familiar with our webinar, as you can see, I am not in my normal location for this webinar. I am down in the heat of the Arizona desert. So, yep, giddy up and all the rest of it. I would like to introduce Kevin Biggie, Aleksandr, Levin, two of our most senior engineers based in the US out of our St. Johnsbury facility in Vermont. And today they will be focusing on a topic related to renewable generation transformers, so optimizing insulation systems specifically for renewable energy generation transformers. As always, if you would like to ask a question, you can click the question mark button or chat box that you see on the left here and enter your question on the right. That will come to both me and the team here at Weidmann, and we will do, as usual, our very best to get to all the questions at the end of the presentation in the Q&A. I do apologize in advance. When we have so many people on, sometimes we get a lot of questions and it's very difficult to get to all of them. But if we don't get to your question today, we will do our best to get back to you in the near future. So without further ado, I will hand over to Kevin, who will kick off the presentation. And I hope you enjoyed this webinar. I will see you again at the end of the webinar for the Q&A. Thanks very much, Kevin. Over to you.
Great, thank you very much, Francis, and welcome everybody. It's great that you could all join us today. And so once again, I'm Kevin Biggie, and talking to you from St. Johnsbury, Vermont, in the USA. And we're happy you can join us today to talk about an optimized installation system for renewable energy generation transformers. So as far as our agenda for today, I'll begin and we'll take a look at some industry trends related to renewable energy and renewable energy transformers. Then I'll talk about some challenges specific to renewable energy generation transformers. And then the next section is a solution, and that's what the webinar is all about, is a solution to the challenges related to these kinds of transformers. I'll specifically focus in on one particular solution, which is a new not so new paper that Weidmann makes as a solution, which is called In Solutions DPE paper, and it has several different benefits. One in particular is the fact that it has a higher thermal class, so I'll talk about that in a separate section, and then I'll hand it over to my colleague Aleksandr Levin, who is going to cover some interesting transformer design concepts, specifically by applying a higher thermal class insulation paper like our Weidmann DPE paper. So, and then we'll wrap up with a summary. So, talking about renewable energy, and so we all know that renewable energy is really growing and taking off. The graph on the left is just a simple illustration of how, for example, wind and solar have grown just in the century from next to nothing in 2000 to, being a significant percentage of renewable energy generation. Whereas hydro and other renewables have held rather steady. And on the right, you can see actually a picture from a recent news release of the world's largest to date solar farm in China, which is 3.5 gigawatts. So renewable energy is, as we all know, growing and continuing to grow. So now let's talk about the transformers for renewable energy. So what do these things look like? So first of all, these kinds of renewable energy sites can have lots of transformers, hundreds of them, in fact, per site. And the other thing is that they're getting larger. So they can oftentimes be rather large in size, several thousand kVA and above, for example. Also voltages and the BIL ratings of these transformers are increasing. And typically these transformers are also constructed with what we call a layer type winding. And some of the bigger ones are again in excess of approaching even 10,000 kVA and higher. So they're bigger, higher voltage, and they're typically layer winding transformers. Great. So when we talk about challenges specific to these kinds of transformers, so first of all, they're intermittent. So the load going to these transformers is intermittent. So the sun doesn't always shine and the wind doesn't always blow. So there's a lot of on and off, so to speak, character to the load that these transformers see. And typically, currently, to deal with that kind of a variable load, these transformers are designed with quite a bit of extra capacity, and so there's oftentimes some excessive capital investments and a bigger footprint needed in order to deal with that. And when you have transformers that are perhaps oversized, if you will, then even when the sun isn't shining or the wind isn't blowing, you can have a lot of no load losses, losses from the transformer just sitting there, so to speak, with losses in the transformer core specifically. So and then finally, as Frankie can attest to in the deserts of Arizona, these sites can often be in hot places. So in particular solar farms, but other ones as well. So when you deal with transformers being in a hot ambient situation, that can reduce the lifespan of these transformers and reduce their reliability. On the right there is a simple graph that's just taken from an IEEE standard on solar transformers, for example, and you can see the dotted line number 3 is kind of showing, an on and off character. So basically from about 8 in the morning until 6 p.m. at night, these transformers are loaded to around 100%, and then at night they shut off. So. And talking about some other challenges. So these transformers are also typically connected to inverters. And so the power coming from the solar panels or often sometimes windmills are going through inverters. And when the power is coming through inverters, you can have harmonics and other power related situations that really increase the thermal, the electrical, and the mechanical stresses on these kinds of transformers. And another thing is with these, again, layer type transformers being larger, so they are insulated typically with paper. And I have a diagram next, we'll show this in a little bit of detail, but these larger transformers, layer type windings with lots of paper. The paper can take a long time to dry for the manufacturers when they're made in the factories, and a long time to impregnate with liquids. So you can potentially have some quality problems just due to the size and the nature of these bigger units. And then finally, too, getting bigger in size. These transformers are also not only larger in size, but also higher in cost. So these are all the challenges. When we talk about layer type winding transformers and paper insulation, this diagram is just trying to depict that. So here you see, for example, a layer wound transformer where you have the low voltage winding, part 1 on the inside, and then you have the high voltage winding in the middle and a second part on the outside. But the majority of the solid insulation separating all of those layers of conductor is paper. So you have paper between the layers, you have paper between the layers in the low voltage and in the high voltage, you have paper that is at the ends of the coils. You can sometimes have extended paper between the high and the low to provide a barrier. Paper between the high and the low as pack out, so to speak. So there's lots and lots of paper in these big layer wound transformers. So when we talk about solutions to these challenges for these specific types of transformers and the fact that they're layer type transformers largely insulated with paper, this paper, this one component of a transformer is actually pretty key and important to defining the size and the weight the footprint and ultimately the cost of these kinds of transformers. The paper also defines heavily the losses and therefore the efficiency of these transformers. And ultimately the paper is the key thing that defines the long-term reliability and resilience of these transformers as well. So with the insulation paper being the key, if we had a so-called engineered paper solution that has enhanced properties, such a paper could provide some opportunities to optimize the performance of these kinds of units. So a paper that could perhaps withstand higher temperatures, a paper that can perhaps dry and impregnate with liquids more quickly at the OEM factory, a paper with improved dielectric performance, and can help reduce the size and weight of these transformers. And most importantly, a solution that is cost effective, right? Every solution is always a balance between performance and cost. So a cost effective solution in particular can not only help with all of these challenges, but can actually do it and actually help reduce the cost of these transformers overall. And so with that, I'd like to introduce you to our specific paper solution, which we call our Weidmann Insolutions DPE paper. So DPE is standing for Diamond Pattern Enhanced paper, as opposed to the typical craft DPP or diamond pattern paper. And so this paper is a special grade of layer insulation for liquid immersed layer type transformers. And so we've engineered this paper to still be made of cellulose. Okay, so it's not craft, right? So typically the paper that's being used and has been used for a long time is craft paper. Craft meaning coming from softwood trees with needles. So we have found some special and unique mixes of other celluloses, because there are other sources of cellulose, and those special mix of fibers and the way that we process the paper yield some performance advantages over the typical 100% craft paper. Yet, because it's cellulose, still the cost point for this paper is also still very, very effective. So in particular, the 4 benefits that I'm going to cover today in a little bit more detail about this paper and what it does, and then specifically what it can do for renewable energy transformers, is it has 4 advantages over the typical craft paper. So number 1, it has a higher thermal endurance in both mineral oil and ester liquids. So that means that it ages more slowly and it has a higher thermal class as a result. It dries faster. So you can potentially have higher quality and productivity when these transformers are being made in the factory. It also impregnates with dielectric liquids faster, similarly quality and productivity improvement potential. And then finally, it has better dielectric performance. And so you can potentially improve your dielectric insulation design with this DPE paper. But again, just to talk one more time about the cost again, that's the important part of this paper as a solution. So if you look at the solid insulation in a typical layer 1 transformer compared to all the other materials, core steel, conductor, the liquid, and other, the tank and such, the solid insulation is really typically representing just a couple percentage of the cost of one of these transformers. And so with DPE paper being 100% cellulose, again, we've kept the cost down, and all of these benefits are achievable at a relatively small price difference on the overall transformer cost, which we say is typically less than 1%. So to get into these particular features and benefits of DPE paper, I'll cover them one by one. So first of all, it dries faster. And we say that typically DPE is drying up to about 30% faster than typical 100% craft papers. And so we've confirmed this in many different ways. We've done several types of laboratory tests. We've done, we did a special study on full transformer coils with a partner, a company of ours, Hedrick in Germany. And on the right, you can see a picture of that particular study with a test coil in there. And the graph underneath the picture, you can see that the blue line is representing measurements of power factor during drying over time, and the blue line representing the DPE coil, and the green representing the craft paper coil, and the DPE coil is clearly drying more quickly. We've also done studies of actual layer wound transformers in OEM factory dry out processes in their factory ovens, and we've also confirmed this to be true. So faster drying, again, it leads to potential quality improvements, less failure rates in the factory, less initial moisture to start with. So the fibers that we use are generally drier to begin with. Than craft, so there's less moisture to remove, and overall this could lead to potential productivity improvements, which as we know, capacity of making these types of transformers is important, and so anything that can be done to make more of them is definitely a good thing right now with all the growth seeing in renewable energy transformers. The next thing is that it impregnates with dielectric liquids more quickly. And so, so we've studied that. In particular, we did a test where we took some liquids and suspended a piece of paper in it, and then heated the liquid and put the whole thing in a vacuum chamber, and we measured how quickly the liquid is rising through the paper. And again, that's where we found that DPE is able to impregnate about 30% faster. With both mineral oil and ester liquids. So again, this is another opportunity to improve productivity in the factory, to improve quality, and in particular for transformers like this that use ester liquids, which are more viscous and can take longer to impregnate. DPE is ultimately an excellent solution. The third of the 4 benefits of DPE paper is that we designed it to have better dielectric performance as a layer insulation in layer wound transformers. So we completed an extensive electrical testing series that took several years to do way back when we were developing this paper, and not only studying the breakdown of the paper in AC voltage, but also for the first time measuring partial discharge inception of layer insulation paper, as well as impulse breakdown. And so the combined results of this study, looking at PD inception, AC breakdown, and impulse breakdown, is that we developed a special set of insulation dielectric design rules specific to DPE, which we can bring to our customers to help with their dielectric design. And so there's the potential to reduce clearances and to ultimately optimize size and cost due to the improved dielectrics with DPE. And then the fourth benefit of DPE paper, I'm going to focus on a little bit more specifically, and that's going to be the subject of the rest of the webinar, and that is that DPE is a higher thermal class paper. And so let me talk a little bit about that. So when we talk about DPE being a higher thermal class paper, so that means it ages more slowly and it has longer life at equivalent temperatures. And the way that you determine the thermal class of these kinds of materials is one of the popular ways is to do what's called a sealed tube accelerated aging test. So you can see some pictures on the right where you see that's a picture of our aging lab with our aging ovens and the aging sealed tube containers, and also a container itself with all of the contents opened up before it. But when you do an aging test where you test the conventional system of mineral oil and thermal upgraded craft versus a new system, we did that according to this IEEE standard C57100, and we found that DPE in mineral oil has a thermal class of 130, which is 10 degrees C higher than TUK in mineral oil. And in esters, it has a thermal class of 140. And again, even these accelerated aging tests, take years to complete. And when you do these tests, what they result in are these so-called life curves. So this represents the tensile strength retention equivalent to the standard system of TUK and mineral oil of these other systems at elevated temperatures. And then you can extrapolate those back to normal temperatures at the IEEE lifetime of 180,000 hours in order to calculate the thermal class. And so that's where we get the thermal classes from. And so what you can do with this higher thermal class is you can actually design your transformers differently. And so in particular, there is a graph about the temperature limits available using IEC terminology, and on the right using IEEE terminology. But just to point out, TUK and mineral oil again is 120 system, whereas DPE in mineral oil is 130, and DPE in ester liquids is 140. And so these graphs in these standards represent what you can do from an average winding rise design, and also from a hotspot maximum capability design aspect as well. So to talk about this in a little bit more detail and how you can apply this elevated temperature capability and higher thermal class, I'm going to turn it over to my colleague, Aleksandr Levin, who will talk to you some more about that. Thanks.
Okay, thank you, Kevin. So I think we can go to the next slide, please. Yeah, so after we introduce the specific features and some advantages of the enhanced insulating paper that we call DPE, so let's explore the application options, how we can utilize this benefit of higher thermal class of DPE paper in layer type transformer insulation systems. And as always in industry, in order really to implement some new ideas, we would like these ideas to be first discussed in details in our engineering societies. And the discussion about the higher thermal class application in transformers actually resulted in development of several international standards. In IEEE, we have IEEE C57-154 standard and also IEEE 1276. An equivalent standard in IEC is 60076-14. So all of these standards actually guide and support application of the higher temperature insulation systems in transformers. Next, please. Thank you. So, as we just discussed, the DPE paper allows to have a higher class insulation systems. In mineral oil, it can result in the 75 degrees average widening rise temperature systems, and in ester liquid, we can increase temperature up to 85 average widening rise temperatures. And again, on this slide, you see the table where the temperature limits are shown for these different temperature class systems. So 65 degree system, 75 degree system, and 85 degree system. So the standards that I mentioned, they actually clearly define what are temperature limits in order to implement such systems. Next, please. So what could be the benefits of application of this higher temperature system, and specifically higher temperature system based on enhanced DPE paper, either in mineral oil or in ester liquids? So the first actually advantage that we can get is extension of the life of transformers. So transformer life generally is defined all other conditions being equal, by the aging rate of insulation paper. And on the other hand, aging rate of insulation paper is defined by temperature of the insulation system. So when we create a system that has 10 degrees additional safety margin in terms of thermal capability, then we theoretically can extend the life of transformer more than twice. And obviously, if we have this additional safety factor, we can increase transformer resiliency against increased ambient and or operational temperatures. So in order to understand why 10 degrees results in extension of life, we can look at so-called Arrhenius life equation. So this is equation that you see on the screen, and it's based on the activation energy theory developed by Swedish scientist Svante Arrhenius. And this specific equation is for thermally upgraded kraft paper in mineral oil. So, and for this system, the maximum long-term temperature is 110 degrees. So, and this equation gives us 180,000 hours of life of insulation at 110 degrees. So if we have 10 degrees additional margin, meaning we let's say go to 100 degrees continuous temperature of the system, then the equation gives us 514,000 hours, which is about 2.8 times longer than at nominal 110 degrees. So this is an explanation why 10 degrees results in more than twice extension of the life of insulation system of transformers. Next, please. So, and the other advantages or other benefit that comes from this higher temperature system is higher overload capability of transformers. So, and this higher overload capability can be used in different ways. We can use this simply by have a chance or have capability to run transformer longer for a shorter time. Or we can design smaller transformer with less kVA nominal capacity, and this transformer still will be able to cover necessary overload capability of such transformers. So if we come back to the graph of the loading of the, let's say, solar power transformers, as you see on this slide, let's try to answer the question, what would be the allowable overload capability for the 100 kVA nominal capacity transformer based on this graph? So we can actually convert this graph in initial load and peak load. So let's say we convert this and we say the initial load is 30% of nominal, and then we have an equation, how much peak overload we can allow for about 8 hours of the peak conditions. Next, please. So if you look at this loading graphs, so we can look at the curve which represent 30% of initial load. And if you look where we arrive with this curve at 8 hours of peak load, we can find that so-called transformer rating factor for this type of loading diagram would be 0.93, which means that 100 kVA transformer with this loading diagram can be run at 100 107.5 kVA for 8 hours. So this is allowable loading capability for 100 kVA transformers with normal insulation system with a peak of 8 hours. So if we simply substitute the thermally upgraded kraft paper with this enhanced DPE paper in mineral oil, then we have this 10 degrees additional safety margin in thermal capability, which actually translates in about 20% higher overload capability. So it means that transformer with DPE paper and mineral oil will be able to be used for with the peak of 8 hours with the capacity of 130 kVA versus 107.5 kVA with normal insulation system. Next, please. And the other way to use this additional thermal capability is to design a smaller transformer. Let's say we need the same loading diagram, or we have the same loading diagram, and we need to design transformers that can be used with this loading diagram. So with the higher temperature insulation system based on DPE paper, we can design smaller transformer, let's say 90 kVA instead of 100 kVA. So this would be smaller size, smaller weight, and hopefully smaller cost transformer. And this transformer still will have allowable peak load of 116 kVA for 8 hours. So we see that enhanced thermal capability of insulation system allowed us not only to design smaller transformers, but also to have a comparable or even higher overload capability. Next, please. So the other concept that I would like to introduce that actually based on the higher thermal capability of insulation system is so-called dual temperature nameplate designs or dual nameplate rating transformers. So if we look at historical analogy, we can recall that thermally upgraded kraft paper was developed in 1950s. And then several years later, this paper was actually recognized by the engineering society, and it was standardized as a 65 degrees average widening rise insulation system. So thermally upgraded kraft paper and mineral oil was defined as 65 degrees average widening rise system. And when this new thermally upgraded paper started to be used in the industry, very often it was used as a dual temperature or dual rating transformers as 55/65 dual temperature rating transformer. So on the right hand picture, you see the nameplate of the old transformer, and if you really look closely, you can see that this transformer has 3,750 kVA capacity at 55 degrees Celsius, and it has 4,200 kVA capacity at 65 degrees Celsius system. And both of these levels are continuous levels. They are just they are possible because thermally upgraded paper was used in such type of insulation system. So again, to draw the analogy with what we are discussing today with enhanced DPE paper, we can say that it's possible to design dual rating or dual temperature transformers with 65/75 Celsius in mineral oil and 65/85 or 75/85 average widening rise in ester liquids. Next, please. So the similar idea, actually, the difference between dual rating system and increased overload capability system is that in dual rating system, the both level of capacity can be continuous levels. So we can run transformer continuously at both levels of nameplate ratings or both levels of temperatures. And actually, this provides actually a good opportunity, especially in cases where we have a very variable load. And as in cases of renewable energy transformers, where load is not constant. And we can really design transformers that utilize better by have these two different levels of capacity at two different temperatures. And the similar system is discussed as a part of EU Green Deal initiative, and it's called Sustainable Peak Load Transformer. So in EU Green Deal initiative, there are really expectation of significant demand in increase of peak load of transformers in coming 10, 20, 30 years because of the electrification of industry and transport and households. So, for example, on the graph on this slide, that came from the discussion on the sustainable peak load transformer, we can see that at the same energy efficiency, the dual nameplate transformer can provide significantly improved material efficiency, meaning significant savings in material at the same energy efficiency. And because we have insulation that can be used at higher temperature, this will not affect reliability or lifetime of transformers. And just to provide us more efficient way to use these available insulation systems. Next, please. So one interesting example was discussed in this sustainable peak load transformer conversation. So here you see on the right-hand side that transformer of dual rating 400 kVA / 440 kVA at 65/95 degrees Celsius can be used instead of 540 kVA transformer or at 65 degrees Celsius. And obviously, this transformer will be smaller, and this transformer will have a less no load losses. But as a result, this transformer will have a peak capacity of the same 540 kVA, and annual total energy losses will be equal to the 540 kVA single rating transformer. Next, please. So this is actually several concepts that can be used just utilizing the advantages of higher temperature insulation system and specifically enhanced DPE insulation paper. So to summarize our webinar today, we discussed the challenges that renewable energy transformers facing today. And we talked about variable loads, we talked about inverter harmonics, we have about high ambient temperature, and that all of these increase thermal, electrical, and mechanical stresses on such transformers. Then we said that these transformers become larger and they have higher and higher voltages. And because they are layer type, they have a lot of paper, and it creates some challenges in production and quality and cost of such transformers. Then we discuss about proposed solution, which is enhanced TPE insulating paper that can be used either with mineral oil or esters. And this paper has several advantages. For example, combining faster dry out, faster impregnation, and enhanced dielectric performance. We can expect improved quality and availability. We can expect reduction of factory acceptance test failure rates and increased transformer reliability and resilience. And then we talked about specifically higher thermal capability of the proposed enhanced system. And the fact that this can be used for optimization of insulation system, high temperature rating design, longer life in operation, higher overload capability, and also interesting concept of dual temperature nameplate designs, or as it's called in Europe, sustainable peak load transformers. So I think this concludes our webinar, and thank you very much for your attention.
Thank you very much, Aleksandr and Kevin. That was a very interesting presentation, and we will move to the Q&A. Speaking of temperatures, it's also rising here as well. So we first of all had a lot of questions coming in, so I really appreciate them. And first of all, just to answer a couple of the usual questions. Yes, we will send a recording of the webinar out that will include the slides and all the details there. If you have any trouble reaching or accessing those because of your company's IT security or whatever it may be, then you can always reach out to anybody at Weidmann, and we can certainly support you there in accessing that information. We also had one quick question that you'll be surprised, Kevin and Aleksandr, that I can answer. Someone asked, are we planning to develop an insulation paper and pressboard similar to Nomex ratings? And of course, we already supply Nomex material. So we're very pleased to be able to service that high temperature market with Nomex. As explained by Kevin and Aleksandr in the last 35-40 minutes, there are different categories of temperature ratings for materials, insulation materials, whether that's liquid or solid. And I think our goal is to capture that full spectrum. So you will certainly be able to continue to buy Nomex material through Weidmann for the coming years for those higher temperature applications. So getting those out the way, now, Kevin and Aleksandr, I'm going to have to ask you the questions that are coming through right now. So first of all, one of the questions we had is with DPE, it's clearly possible to increase the thermal class between layers, but what are the alternatives for cooling ducts for high temperature insulation system? Something here saying cooling ducts are manufactured with pressboard, that is not a thermal upgraded material. So with the mix, is it possible to achieve a hybrid insulation class 140 with a top oil maximum of 65 degrees C?
I can maybe answer that one. So, so yes, the answer is that you know, the hot spot of these kind of layer wound transformers is being, you know, seen by and as affecting the layer insulation paper specifically. And so the other materials, for example, the duct strip cooling sticks, you know, they're not necessarily in the hot spot. And so therefore, typically duct strip does not have to be a special material. So a hybrid solution where DPE is a layer insulation, but with standard duct strip and even standard pressboard, you know, components for example, insulating the coil from the core. That hybrid system can still have these extended thermal classes. And actually, there's details about what I just said in the IEEE guide, IEEE 1276, which Aleksandr covered in his first slide. So there's actually a figure and some details about how DPE can be used as a component in a hybrid system with standard duct strip and standard press board to still enable these higher thermal class systems.
Okay, thanks, Kevin.
And if I can, Francis, at the very end of our presentation today, we have a list of references, and I would recommend really to go and get familiar with these documents, which are mixed between standards and published papers, and they actually explain pretty well how this type of hybrid system can be used.
Okay, thanks. Yep, thanks for the clarification, Aleksandr. Okay, next question. So in the case of DPE, can you use the same measurement for the DP value to characterize the end of life of that paper? So today around 200.
Yeah, I can answer that one.
Yeah, go ahead, Ken.
No, I guess I can answer that also. So being cellulose, okay. So the current degree of polymerization test that we do for typically kraft paper can also be used on DPE paper. So DPE paper can have a degree of polymerization measurement done on it. As a matter of fact, DPE and the fibers that we use actually has a significantly higher starting DP to begin with. So that's another benefit that you'll find with DP paper is that it itself has a higher DP value from the beginning.
Okay, thank you. Let's try and get through a few a little bit quicker. How does this paper react to acidity in ester cases compared with kraft paper?
Yeah, I mean, I would say that it's pretty equivalent. Again, so this is cellulose paper, and we would expect this reaction to be very similar to kraft paper reaction to acidity.
Okay, thank you. We had a question, a usual question, the Weidmann design curve. Do we have one on DPE and ester liquids, and do we plan to publish it? I will answer that one. You can contact our engineering team. We do have a significant amount of research on ester liquids and design curves. We're not publishing them all out into the general market right now while our research is ongoing, but you're more than welcome to contact our engineers and have a discussion about that with them. So I hope that answers your question.
Great answer.
Thanks, Kevin. Right. I've got a fairly straightforward question. Is paper used, is DP available in 2, 2.5, 3, and 5 mil without the diamond dot adhesive pattern?
Yeah, I mean, yeah, Kevin, go ahead.
Yeah, no. So as layer insulation paper, it's typically offered with the epoxy diamond pattern adhesive because that layer insulation material, you want those epoxy dots there for the short circuit strength of the coil. However, we do realize that some of these kinds of transformers, that the high voltage wire in particular can be insulated with paper instead of with enamel, for example. And so you can use thinner DPE for those applications, even with the dots typically. As far as being offered without the dots, that's something that we could discuss, as a future potential. Yes.
Okay, thank you. Another question, what will be the reference temperature for load loss correction when using DPE with 75 degrees C? winding rise?
Yeah, I think what is really discussed right now in standards, if you talk about increasing a temperature of insulation system by 10 degrees, I think it will not affect the reference temperature for calculating of no load losses.
Okay.
And I
Thank you.
think in engineering consensus so far is that we can use the same reference temperature.
Okay. Thank you. Next question from our friend at Mega, Diego. Hello, and thank you for your kind words to the team. As the paper ages, we're used to seeing TUP and test oil for furans or methanol to estimate the age. With this material, how do we estimate aging without taking samples for DP, and what is the correlation?
Yeah, I mean, again, the one of the things one of the good things about DPE is that it's still cellulose. It's still 100% cellulose, and so a lot of the same type of analyses that you do on craft cellulose paper in terms of oil analyses can be done. So there's not a dramatic shift because it's using some totally completely different fundamental fiber. It's still cellulose. But as far as the exact details about that, I don't know if we necessarily have the data at this point to say, but it's something that we could certainly look to monitor.
Okay. Thanks, Kevin. And quick question, will DPE with mineral oil and DPE with ester liquids be added to any new updates to IEEE or IEC standards?
Yeah, we are working on that as we speak. One of the references that Aleksandr had in his first slide again was this IEEE guide for the use of high temperature insulation materials, which is IEEE 1276. And I'm currently the chair of a working group to revise a portion of that standard. We're going to amend one of the annexes, specifically talking about a high temperature insulation system aging examples. And in there, we have some new reference material going in that is talking about DP paper and its capabilities. So yes, there will be some information. We hope to finish that draft soon and have it published shortly thereafter.
Okay, thank you. Quick question on the curing and sticking of DPE. Somebody's asking what the curing point is and whether we see any differences in standard coated craft paper versus DPE. And I just want to add before you answer the question about curing point there and any differences, that if anybody has any specific questions on performance for adhesives used, you can always contact Weidmann's account manager or our technical team here. So Kevin, curing point, and do you see any differences with standard craft paper that's coated for adhesion?
No, that's a really good question. So we actually have several coated papers that we offer at Weidmann, several grades of base paper that are still coated in the same process and with the same epoxy resin dots. And so really the base paper is really independent from the bonding and curing of the epoxy dots. So in fact, DPE is going to cure in exactly the same way as all of our other coated papers, again, because the process of coating and applying the epoxy dots is the same process. It's the same epoxy. So our standard recommendations that we have for curing and bonding apply to the whole family of our coated papers. We actually have a very good and simple reference document that discusses bonding and curing of our papers. And if somebody has a particular question, we'd be happy to provide that reference as needed.
Yep, there was quite a few questions around that, so I think that would be useful maybe to send that out potentially at the end of the presentation, Kevin, with the other material and the references.
Perfect. Yeah, that sounds great.
I will just ask a couple of final questions. Aleksandr, I'm not sure if this one from our friends at SGV Smith is one we can answer right now, or whether we need to take it offline, but they asked, do we have some values about the insulation life considering oxygen and water effect according to IEC 60076-7 2018 Annex A? You can comment to it if you'd like, or we can certainly take that question offline and provide some information to SGB.
Yeah, I mean, it's obviously that oxygen affects the life of insulation materials. I would say I don't think we have any specific answer, but I would say the effect of oxygen on DPE would be pretty similar to the effect of oxygen on other cellulose kraft materials. So, I don't really forecast any difference, but obviously it should be taken into account.
Yep. Okay, thank you. And then the final question that I'll ask for today is relating to, well, first of all, I will answer a quick question. Someone asked if DPE is only used in renewable transformer applications. And the answer to that is no. It is very popular for using in distribution transformers and certainly critical distribution transformers. And we have a lot of use cases where ranging from large investor-owned to co-op and municipality utilities are actually specifying DPE now for all distribution transformers. So if you'd like further information on that, you're more than welcome to reach out to your account manager or our technical team, and we can cover that. So that covers that off. And then on the topic of applications, Kevin, and I'm not sure how much or whether you can say anything about this, but of course the question came, DPE is used typically in distribution size transformers. Do we have anything in the works for the power side of our business, a similar thermal class material?
Mm-hmm. Yeah, so yeah, that question has been asked. If there's an equivalent, solution being worked on for power transformers, and in power transformers, the paper that is wrapped around the conductor wire in power transformers is really the insulation material that is seeing the hottest spot. Kind of the equivalent of the hot spot in a layer winding transformer. You have the paper, and so yes, we do have in the works to bring a solution for that. And anyways, we have this example in DPE, this example solution, and so we're very excited that we can take all of our knowledge and learning about the use of DPE and layer winding transformers and its improved aging and everything that we've learned and take that to our current developments in a wire wrap paper. So we're excited about the future of that, and there should be some news on that in the near future.
Okay, thank you very much, Kevin. All right, well, just to wrap up today, first of all, let me apologize. We've still got a lot of questions coming through, people referring to specific issues that they're having with solar transformers, 6.25 MVA transformers. We'd be more than happy to try and answer that question for you offline. Unfortunately, we have 38 seconds left here. And also Siemens Energy, I saw a couple of questions come in from your side and specifically about, do we have real case transformers in operation with DPE? To answer that, there's hundreds of thousands in North America that are using DP. I think we're probably close to 250,000 there. But your question was specifically, I think, about have we looked at the difference in performance and so on. So again, apologies we didn't get to that, but please feel free. You will get a follow-up email from either myself or someone on the team. Feel free to reply to that, and we will certainly do our best to get back to you and give you more information. So if you do need any further information or an additional meeting, I'm seeing questions come through as we go. Wire wrappings coming through. Please feel free to contact us. You can reply directly to the follow-up email or reach out to your account manager. It's getting hot and I think I'm melting here, so I look forward to being back in cooler climates for the next webinar. Thank you again for joining, and wherever you are in the world, I wish you a fantastic continuation of your day. Thank you, Kevin. Thank you, Aleksandr, and we look forward to seeing you again soon.
Thanks everybody.
Bye-bye.
Thanks for joining. Thank you very much.